As the question says, a particle of mass m is kept on the top of a smooth sphere of radius r. It is given a sharp impulse which imparts it a horizontal speed v. Then find the normal force between the sphere and the particle just after the impulse. What should be the minimum value of v for which the particle does not slip on the sphere, and assuming the velocity v to the half the minimum calculated in part B, find the angle made by the radius through the particle with the vertical when it leaves the sphere. So what's happening is that there is a sphere of radius r on which a block has been kept. Now suddenly an impulse is given to this block to give it a velocity or speed of v. Now this is the tangential velocity over here, and we can also say that it is the net velocity over here for this particle. So we can make the equation for this, in which we are having the mg in the downward direction and the normal reaction in the upwards. So the centripetal force that is towards the center, mv square by r equal to mg minus n. Finding the value of normal reaction, it comes out to be mg minus mv square by r. So this is the answer for the first part of this question. Let us now proceed for the second part of this question, in which we need to find the minimum value of v for which the particle does not slip on the sphere. Now for the particle, if we look at with respect to the sphere, then a centrifugal force F will act outwards. There will be a normal reaction N and an mg in the downward direction. Framing the equation over here, we get that the centrifugal force plus normal reaction equal to mg. Now to avoid the slipping on the sphere, then normal reaction becomes 0. That means it becomes out of contact for this sphere. So simply F will be mg, that is mv square by r equal to mg, giving us velocity equal to under root gr. Proceeding ahead with the C part of this question, in which they have given us the velocity half of the minimum calculated in part B, that is v by 2, and we need to find the angle. So we are having the v1, let this velocity be v1, then it is under root gr by 2. So v1 square is actually gr by 4, right? Now let us suppose that the velocity when the block leaves the contact with the sphere is v2. Then we can write the equation as mv square by r at that point, that is v2 square equal to mg cos theta. Why it comes out to be like this is, this is the sphere, this is the initial position, this is the position where the block leaves the contact, this is v2 over here, v1 over here. If this makes an angle theta with the vertical, mg is downwards, then this will be theta by alternate interior angles. So a component mg cos theta will be towards the center, giving us the equation of this. Now from here we get v2 square equal to rg cos theta. Let us mark this equation as equation number 1. Now also we can apply the work energy theorem, for which we can write it as half m v2 square minus half m v1 square equal to work done by gravitational force, which is mgr into 1 minus cos theta. This comes out by r minus r cos theta. So this gives us the height by which it has descended, right? So this gives us the equation of v2 square equal to v1 square plus 2gr into 1 minus cos theta. Now let us put the value of v1 from here to here and mark it as equation number 2. Now from equation number 1 and 2, let us equate the values of v2 square giving us cos theta equal to 1 by 4 plus 2 minus 2 cos theta, or cos theta equal to 9 by 3 into 4, giving us theta equal to cos inverse 3 by 4. So this is the angle where it will slip out.